Hello, Honor Chem students. Today what we're going to talk about are systems and surroundings, which are really an important piece in our understanding of thermodynamics. They apply to a lot of things besides just chemistry. Like if we are talking about an internal combustion engine, which is the thing that gets us to school every day, or used to get us to school every day, unless you walk to school, the system would be the internal combustion engine, and the surroundings could be like the hood of your car, the wheels of your car, you in your car. And that is all part of what we study when we talk about heat transfer. In chemistry, when we talk about systems and surroundings, what we're typically talking about is the chemical reaction, which you can see right here. So typically, the system would be a chemical reaction, and then there's something bounding this system, like, for instance, maybe the beaker that the chemical reaction's happening in. And then the surrounding is everything else. So it would be the air in the room, it would be the table, it would be you, it would be the pressure of the room, the air temperature of the room, anything else that would be outside of what it is that you are studying. That's what we call the system, okay? So just some very quick terms about systems and surroundings. If we look at a chemistry example, and I'm going to talk about that ice and water example, which I have right here. Again, you'll notice that you've got an ice cube in the water. So let's say you are wanting to observe the heat transfer in the ice as the water melts. And remember what we talked about the other day is that what's going to make this melt is that the cube from the water is going to go into the ice cube, because heat always goes from a warm body to a cold body, and the water temperature is warmer than that ice cube, right? So that's what makes the ice cube melt, is the heat transferring from that warm body to the cold body. So a chemist may be observing the heat transfer in an ice water as the ice melts. The water is the system, and the ice cube is part of the system, but everything else is the surroundings. So even though the boundary is also considered to be the surroundings, so the cup, the air outside, you watching this experiment, that would all be part of the surroundings, okay? So another couple terms that I want to talk about that are important in thermodynamics or thermochemistry, which is what we're studying, is this word, and I noticed that I spelled it wrong, so let me fix that here. This is endothermic and exothermic reactions. So the difference between endothermic and exothermic reactions. And this is where we're going to get into an idea of the negative sign, which I alluded to in earlier lessons, and today we're gonna talk about what that really does mean. Okay, so an endothermic reaction means that energy is going from, and actually this is the picture, so they kind of are backwards here. This is the picture that means endothermic, that actually in an endothermic reaction, energy is going from the surroundings into the system. So heat is going from the surroundings to the system. You as an observer, how would you notice that? Well, let's say that you take an initial temperature and it's 20 degrees, and then you put some salt in here, and then the temperature goes down. Well, that means that the energy went from the surroundings into the system, and that would be an endothermic reaction. An exothermic reaction here, which is this picture here, means that energy is going from the system to the surroundings. This is very common. About like 90% of all chemical reactions are exothermic. Only a few of them are really endothermic. So here, let's say you're putting acid and base together, and the temperature increases. That means it is an exothermic reaction. So we're going to also talk about these pictures here, which we call enthalpy diagrams, or I call them PE diagrams, and you're going to learn how to draw those, okay? This is a picture of an enthalpy diagram of something that you may have some background knowledge on. It's if you strike a match, okay? So if we're to strike this match head right here, okay, so imagine that I strike it, we know that it's gonna go on fire, and when you put your hand over that flame, you feel heat, right? Well, where's that heat coming from? It's coming actually from the chemical bonds that were in this match head. And it's releasing from the system to the surroundings. So energy is going from the system to the surrounding, and that's what we would call an exothermic reaction. Okay, energy was going from the systems to the surroundings. You know energy was being released because you felt that heat when you put your hand over the flame. Okay, so how do we diagram these things? Well, it's pretty simple to do. There's two types that you're going to have to know: how to diagram an exothermic reaction or how to diagram an endothermic reaction. So the first thing I want you to think of is exothermic. Okay, well, what does it mean to be an exothermic reaction? Well, it means that energy is released, and it's released from the system to the surroundings. Okay, so I'm going to just write this very quick because I don't want to waste all my time doing this. And I probably didn't spell that right, but you know, that's par for the course. You guys are used to me by now. So energy is released from the system to the surrounding. If we take a look at that, you'll notice that energy is on the reactant side, or I'm sorry, product side. So energy is on the product side, and it's incorporated in the chemical reaction, if you will notice. So it's on the product side. Product is what that says. And the last thing is, if we were to pull out what we call the energy, and we're going to learn energy has this name called delta H, that actually stands for the word enthalpy, which means the same thing as energy at a constant pressure. If we were to pull that out, the delta H is negative, okay? So how we draw that is we would draw the reactants up here, and we would draw the products in a line down here. And I like to put R here to remind me that this is reactants, and a P here to remind me that that is products. Notice my axes, this says potential energy in kilojoules, and then the x-axis, it says reaction time or reaction progress. And then you write the two reactants up here, CH4, and by the way, I'm sure this isn't balanced. I'm actually quite sure it's not balanced. Let's see, one carbon. I think I need to put a 2 here, 2 waters. And that gives me 2 of these. And now I am balanced, so I'll put my 2 waters there. And the products are CO2 plus water, okay? And this right here, this difference right here represents what we call the delta H. And if we were to incorporate that delta H, it would be a negative 890 kilojoules. That is because we pulled it out of the equation. We know that it's exothermic because energy was being released, okay? So just so you know, there is another way to write this equation. See, you can write this equation as CH4 plus 2 oxygens going to, oh, there's the arrow sign, going to CO2 plus 2 waters. And if I were to pull out the energy term, I would say the delta H is equal to a negative 890 kilojoules. That negative doesn't really mean that there's negative energy. There is no such thing as negative energy. The negative sign just tells you the direction the energy is moving. So it tells you the direction the energy is moving. That's the purpose of that sign, okay? All right, so that's an exothermic reaction. Let's take a look at this endothermic reaction. For endothermic reactions, we know that energy is absorbed. So what that means, that energy is going from the surroundings into the system. These are not as common as exothermic reactions. You'll notice that energy is on the reactant side. And you will also know that when we pull out the delta H, it is positive. Okay, so let me make a positive sign there, make that better. Let's just put, okay. So when I draw this, now what's going to happen is my reactants are down here and my products are up here. So this would be the reactants, this would be the products, this is the calcium carbonate, this would be the calcium oxide plus the CO2. And you will notice that when I type in, or I look at this difference right here, the difference right here between the two, the delta H value would be a positive 570 kilojoules. Okay, so that's showing you an endothermic reaction. That's how you draw enthalpy diagrams, or what we call PE diagrams. So just so you know, they have the same name, so sometimes they're also called or considered to be, let's see if I can write that in here, they're called enthalpy diagrams. That means the same thing, okay? So good luck, you guys. Continue on your learning. There's going to be another short video on how we do calculations with this. All right, talk to you guys soon.